Hello, my name is Ernest Blatchley. I'm the principal scientist responsible for process engineering at Excimer. I'm also the Lee A. Reith Professor in Environmental Engineering at Purdue University. I'll be presenting today on human-safe near-field infection protection for continuous pathogen inactivation in air and on surfaces. I'm giving this presentation on behalf of my co-authors, Carl Linden from the University of Colorado and Joel Ducoste from North Carolina State University, as well as the rest of the team from Excimer, who I'll introduce later. If we consider the current situation with respect to infectious disease preparedness, it's clear that airborne pathogens represent threats to global health as well as economic security. COVID-19 in particular has restricted interpersonal interactions, and the health guidelines that have been implemented to combat COVID-19 have been met with some resistance. This is complicated by the fact that current PPE, which is an important technology that we use to try to combat COVID-19, is based on outdated technology that yields variations in performance. Moreover, the demand for PPE has resulted in short supply, exorbitant costs, and solid waste disposal issues. To resolve this issue, we're in the process of developing near-field infection protection devices that are based on far UVC radiation to protect an individual's personal space. The incorporation of far UVC radiation, which for purposes of this presentation will be centered at 222 nanometers, into wearable and portable devices will accomplish rapid inactivation of pathogens in air and on surface to provide an invisible bubble of clean air around the user. Before I get into the details of the work that we're involved with, first I want to define some terms, the basic nomenclature that accompanies UV radiation. The International Union of Pure and Applied Chemists has defined UV radiation as electromagnetic radiation with wavelengths between 100 and 400 nanometers. That's further subdivided into three regions, UVA, UVB, and UVC, which respectively include radiation with wavelengths from 315 to 400, 280 to 315, and 200 to 280 nanometers. Germicidal UV radiation is generally associated with the wavelength range from 200 nanometers to 320 nanometers. Radiation in that wavelength range is known to cause damage to critical biomolecules, including nucleic acids, DNA, and RNA. And at wavelengths less than about 240 nanometers, we also see that protein damage becomes important. Our focus is on a subset of the germicidal UV range, specifically what's commonly termed now as far UVC radiation. That is radiation with wavelengths between 200 and 230 nanometers. Now, I want to point out that this is not a formal definition that's been accepted by any professional organization, but it is a description, an informal description of a wavelength range. What's relevant about the radiation in this wavelength range is that it has minimal potential for damage to mammalian tissues, specifically the skin and eyes, yet it's very effective for disinfection. That combination of characteristics represents a potential game-changing set of characteristics with respect to implementation in disinfection technologies. To elaborate a little bit on the lack of potential for far UVC to cause damage to skin and eye tissues, we need to consider how that radiation penetrates into those tissues. First, focusing on the skin. If we compare penetration of conventional UVC radiation, often at 254 nanometers, with far UVC radiation, here illustrated with 222 nanometers, what we observe is that the conventional radiation will penetrate deep into the skin tissue and will involve the germinative cell layers, whereas far UVC, 222 nanometer radiation, will only penetrate into the stratum corneum, which is a layer of dead skin cells on top of the germinative layers. A similar set of arguments holds with respect to the eye, where we observe that there's minimal potential for penetration of far UVC beyond the outer layer of the cornea, whereas 254 nanometer radiation, conventional UVC, will penetrate more deeply and therefore has the ability to cause more damage to that tissue. Collectively, that information informs what are known as the threshold limit values, or TLVs, which define exposure limits for UVC radiation. Now, these limits are defined based on wavelength, with the peak wavelength being recognized at about 270 nanometers in terms of its ability to cause damage to these tissues. That's characterized by what's called the relative spectral effectiveness. And again, you see that the maximum value occurs at about here, 270 nanometers. At either shorter or longer wavelengths, the damage to tissues diminishes. Now, the black line is a line that was originally presented by the American Conference of Governmental Industrial Hygienists, or ACGIH, and they recently have proposed updates to that guidance for both the skin and eyes, which are illustrated by the green and red lines respectively. In turn, that information informs 8-hour exposure limits for radiation as a function of wavelength. Again, we see the minimum exposure, because of its maximum sensitivity over here, occurs at 270 nanometers. Our focus is here at 222 nanometers. And what's relevant to point out is that the existing guidance for 8-hour exposure is 23 millijoules per square centimeter. In other words, that's the dose of radiation at 222 that ACGIH and other organizations feel you can be safely exposed to in an 8-hour day. But more recently, they've updated that with a proposal to suggest roughly an 8-fold increase for exposure to the eyes and roughly a 20-fold increase for exposure to the skin. Again, that information suggests that this far UVC radiation could be incorporated into game-changing technologies, because now it's possible to expose humans while at the same time exposing microorganisms. The common sources of far UVC radiation are generally krypton chloride Excimer lamps. So here are 2 of these commercially available lamps. They're available in a wide range of geometries and form factors so that they can be incorporated into a wide range of products. Their output spectra look like this. Here there are 4 spectra illustrated. The solid lines represent these lamps without an optical filter. And we see that those output spectra for the unfiltered lamps have a dominant primary peak centered at 220 nanometers, with a secondary peak over here at 258 nanometers. This peak is what we refer to as far UVC radiation. The secondary peak over here has the potential to do damage to human tissues. So commonly these lamps are operated with an optical filter, and the dashed lines here illustrate what happens to the output of these lamps when they're subjected to these optical filters. This is perhaps more clearly illustrated on this graph, where the same data are now presented with a vertical axis that's on a log scale. And here again, what we see is that this secondary peak, which is relatively small to begin with, is decreased by roughly a factor of 100 by the inclusion of these optical filters. Now, with respect to disinfection, let's consider how these respiratory viruses that we're so concerned about now respond to UV radiation at 222 nanometers. The blue dots in this graph represent the responses, measured responses for various coronaviruses. On the vertical axis, we have the fraction of those viruses that retain infectivity on a log scale, presented as a function of the 222 nanometer dose that's delivered to that population of viruses. The dose is defined as the fluence rate by the time of exposure. When we consider these respiratory viruses, what we observe is that in general, we'll get at least 3 log units of inactivation, or in other words, 99.9% inactivation, at a UV 222 dose of less than 5 millijoules per square centimeter, which is a very small dose that's easily delivered. So the take-home message from this slide is that we require very low UV doses to inactivate these viral pathogens. And the coronaviruses in particular are among the most sensitive pathogens to UV radiation. Now, one of the problems with working with those viruses is that they are pathogenic. They can cause disease and they're dangerous to work with. So we're also working with surrogates for these viral pathogens. The surrogates that we're working with are all phage, and it's important to recognize that phages are viruses that have the ability to infect bacteria. They have no ability to infect human tissues. That makes them safe to work with. But the phage that we have chosen here have responses to UV radiation that are similar to the coronaviruses, which are again indicated by the blue dots here. The surrogates that we're working with are indicated by the red symbols or the gray symbols over here. And again, the take-home message from this slide is that their responses to UV-222 radiation are similar to the coronaviruses and other airborne pathogens, and all of them are slightly conservative with respect to SARS-CoV-2, which makes them good candidates for use as these surrogates. Next set of tools that I'd like to present are numerical simulations. These are simulations that capture the relevant physics that govern the behavior of UV systems that are used for disinfection. These tools are used widely to investigate so-called what-if scenarios, and they inform the design of reactors. They can be used for troubleshooting, and more generally, they can be used to more completely understand the physics and process dynamics that govern the behavior of these systems. To illustrate, here's a simulation of fluid mechanical behavior in a UV disinfection system that's used to treat water. So this CFD simulation resolves the flow field in the system. When that's integrated with a similar simulation of the irradiance field for a reactor like this, as well as kinetics for inactivation, we can then predict and very accurately simulate the inactivation response of a given pathogen to exposure to UV as it traverses this reactor. Now, this approach is something that's not limited to liquid systems. It can be used for other applications. So here's an illustration of an experiment that we'll be conducting in my lab, where we're going to be measuring the intrinsic kinetics of inactivation of aerosolized viruses. We'll introduce a virus suspension as aerosols using a nebulizer. That airstream will pass through this quartz channel that has a number of these optically filtered krypton chloride Excimer lamps on them, and then we'll collect samples downstream using a bioaerosol sampler. So that's an experiment that allows us to examine the intrinsic kinetics of this inactivation response for these aerosolized viruses. We can also simulate that on the computer. So here's the flow field for this system. Here's the fluence rate field for this single lamp being illuminated. And when we integrate that information with the kinetics of inactivation, we can then predict the inactivation response of the viruses as they go through this channel. So having the ability to conduct the experiment and perform the simulation allows those tools to be expanded to other applications. So for example, the development of the products that we are working on. So here's an illustration of two people. One of them is invisible. The person on the left has coughed or is breathing and basically is emitting viruses toward the second person. The second person in this simulation is wearing a device that we're working on. And the basic idea is that the fluence rate field from the lamp on that device can also be accurately simulated. When that information is integrated again with the intrinsic kinetics of inactivation, we can simulate the inactivation field around the person who's being protected as well as the source of radiation. So the basic idea here is that with these additional capabilities, we can develop cost-effective, optimized solutions for providing human health protection. So the basic idea with this approach that I'm outlining here is that we're applying process engineering principles to inform future decontamination efforts. What I mean by that is we're going to decompose the problem into its basic units, its basic elements, define that behavior with respect to those basic elements, and then integrate to develop solutions. So for example, those basic units include examinations of the far UVC sources that are available for implementation. There are a number of new and emerging sources that have been developed related to far UVC, and as I mentioned before, they're available in a wide range of geometries and form factors that allows their incorporation into these small mobile devices. Second, we're looking at the fundamental biology, quantifying the inactivation responses of the pathogens and surrogates, and using that information to inform how we understand these viruses to respond in aerosolized respiratory fluids as well as on dried surfaces. And then lastly, as I mentioned before, we're going to integrate that information to optimize the use of this 222 nanometer radiation for decontamination. Moreover, these devices can be developed as smart devices that can be embedded into public systems to provide coordinated, multi-layered approaches for biodefense. And lastly, I should mention that the methods that we're using here are not constrained to small-scale applications like PPE, but they can also be expanded to larger scale applications. So to conclude, I'd like to highlight the team that we've assembled at Excimer. The team brings a wealth of experience and a breadth of experience and expertise that relates to entrepreneurship, government activities, fundamental physical sciences, and engineering. And again, we've been intentional in assembling this diverse team so that we can provide holistic solutions to these near-field protection devices. With that, I'll conclude and suggest that if you have questions or comments, please send email to Rick Rosansky. He is the CEO of Excimer. His email is illustrated here at the bottom of this slide. Thank you for your attention.